Hi, everyone. Hi, my name is Sneha Nguba, and today I'm going to talk to you about my journey with networking and Go, which has been really just been a very multi-layered journey, puns fully intended. So, just a little bit about myself. I'm a software engineer. I work on the networking team at DigitalOcean. If you're not familiar, we are a cloud hosting company. We have about 14 data centers located around the world and a host of products such as Droplets, which are essentially virtual machines, Kubernetes as a service, database as a service, VPC, lots of exciting different things for developers and businesses to use. So, I'm going to talk to you a little bit about my journey in this industry today. So, back in 2016 was when I actually first started learning about Go. So, I first started learning about Go and started working with Go when I joined this company. So, what is Go? If you're not familiar with it, it is a language created by Google. It is designed as a systems language used in a lot of different verticals and at a lot of different cloud providers and just in general in the infrastructure space, and is meant to increase developer productivity. So Go is a statically typed, memory-safe, compiled programming language. So the type is known at compile time, not necessarily runtime. And in terms of memory safety, this is just in comparison to other systems language where pointer arithmetic is allowed. Furthermore, Go handles a lot of the allocation and garbage collection as well as memory access checks. Go also has excellent concurrency support through the use of multiple primitives. So there's something called Go routines, which are lightweight processes that are multiplexed onto operating system threads. Of course, if you aren't careful, you can be a little abusive with Go routines as well. There's also the sync package, which is part of the Go standard library and has a lot of concurrency primitives such as mutexes to kind of lock and unlock access to a shared memory resource, thread safe maps, as well as something called actor Go routines, which has to do with the actor model. Furthermore, there's something called channels, which are maybe, I mean, people are very opinionated about channels. Some would consider it a very exciting element of Go. It's a primitive through which you can send and receive data with a typed operator. Whereas others also, similar to Go routines, channels are something that can also obviously be abused within this language. So beyond that, Go is syntactically very simple. Before using Go, I had written a lot of code in C++, and just in comparison, I found that just getting up to speed on new code bases was quite easy. Furthermore, it enforces a coding style. So after I had learned Go that year, then I started working on developer tooling at this company, and that includes things such as Kubernetes, Prometheus, doing things with logging. And around this time, I learned about this concept of microservices. So the industry was kind of, I guess, a few years ago, moving really heavily away from monolithic services and monolithic repositories and applications to a lot of these microservices that were loosely coupled, easily deployable. But the problem is when you break down your monolith into a lot of microservices, quite often you need to somehow manage them. And that's where containerization came in. So we needed to containerize them, but we also needed to manage and schedule them. And so that led us to Kubernetes. But instead of just using Kubernetes as is, we built an abstraction layer on top of Kubernetes known as DOCC. But now that we have, these containers within these pods, which is this construct in Kubernetes, running on a bunch of different nodes, also with a control plane and networking, we realized that we needed some observability in our lives. And so that led us to the three pillars of observability, including tracing, logging, and metrics. So when it comes to metrics, we started using Pandora, which essentially was a functionally sharded data center-wide Prometheus setup. I think there's quite a few talks out there from various colleagues about how we've actually constructed Pandora, and it's pretty neat. I would highly suggest you check it out. So here's an example of some dashboards that we've constructed for different applications using Prometheus. In this case, the dashboards are in Grafana. We also started using Lightstep as our tracing backend, and this was very helpful in kind of debugging latency and any performance issues. But then finally, logging is something that we still needed. At the end of the day, we have less retention for logging, perhaps because it's quite expensive to maintain logs for an infinite period of time. However, when it comes to debugging needle in the haystack type issues or particular errors within an application or a microservice, logging is really where it's at. So now that I learned about Go, I learned how to, containerize my Go microservices and observe them. I realized that I kind of wanted a new challenge in my life, and that is what led me to moving towards networking, which is a different area of the company, but especially I believe at an infrastructure provider such as DigitalOcean and a cloud hosting provider, it kind of gets you closer to customer products as well. So in the first year of joining networking, I worked on DHCP and a product called Gateways. So when I first joined, because I didn't really have a computer science background, a lot of these concepts were fairly new, and I really had to dive into them now that I was working with a lot of these protocols. So one of them, the OSI model. What is that? Another one, what exactly is a socket? And then finally, I was also learning a lot about different existing protocols, including some of these DHCP, ARP, Neighbor Discovery Protocol. And that finally led me to, the last 2 years as a network engineer, where I kind of diversified what I was working on. Outside of DigitalOcean, I started working with some friends just to have fun in trying to re-implement these like basic network primitives that we often use, but we don't necessarily write just because they already exist. For example, a load balancer, layer 7 or layer 4 load balancer, port scanner, which is similar to the utility tool Nmap. And then this year, I started working on another area of networking, something that another product called private only droplets. So that actually brings me to the subject of my talk. Super excited Husky meme here, which is how and when to use Go to build networking primitives. So the plan for today is that we're first going to talk about why use Go. Of all the languages in consideration, why might you want to use Go? Secondly, we're going to dive into the networking stack. And for those of you who don't necessarily have a networking background, we're going to talk a little bit more about different elements of networking. And then finally, we're going to actually go into the examples. And I always like to think the best way to learn is by doing. So we'll dive into several examples of things that I've actually worked on, which were instrumental in helping me learn more about networking. So yeah, let's start. So starting with why should we even use Go for networking services? Quite a few reasons. And some of these I think I already mentioned earlier when I mentioned I started learning about Go and started using it. So one, concurrency support. Go has a lot of great concurrency support through the sync package as well as other third-party packages. Some of my colleagues also argue that Go is extremely easy to fuzz test, which is vital when it comes to building networking tools and I guess networking services that quite often have input data. It's also extremely easy to build CLI tools. Just by the sheer volume of third-party packages available, it's quite easy to construct these. And this is something that I've done on multiple teams within this company. It's also very easy to write RESTful and gRPC-based services, which is something that we also do at DigitalOcean. And finally, it is a server-side language. But Go isn't always the right answer, and I think that's something important. I think quite often those of us in this industry have a tendency to be very zealous when it comes to our languages, but not every language is the right fit for every use case. And I think one example is when you really need to do high performance packet processing. I think that the tendency to need to unmarshal an entire packet in Go versus how things are handled in C with just reading things off the wire is a little different. And so if you really needed to do super high performance processing, for example, receiving 1 million packets per second, I think there are other languages, such as C, that might be more efficient and might be more applicable for your use case. But why did we use Go? And this once again harkens back to what I had mentioned earlier. We have a monorepo. This is also, I think, a contentious thing within this industry. But in our case, I think the monorepo has really helped us. It's really helped us to develop some standard coding packages or standard coding practices. And furthermore, we do have shared packages that have made it very easy to onboard new developers to the company. So beyond that, we do use a lot of gRPC and a lot of CLI tools. So just even on the hypervisor, for example, within the cloud, a lot of virtual machines are on a single hypervisor. Within that hypervisor, we do use a lot of CLI tools for different debugging purposes, or just part of the overall network stack. Furthermore, performance was already good enough. And I think this is something that we often forget as engineers. We try to just see benchmark and try to determine the limit and try to constantly optimize, but there's no need to optimize before you have a problem. And in fact, with one of the services that we wrote in Go, the performance was comparable to a Juniper ARP handler. So I think that really just was sufficient for our use case. So that brings me to the fun part, the networking stack. So what is the OSI model? This is something I mentioned earlier. It is called the Open Systems Interconnect model, and it's a framework that allows us to describe the functions of a communications network. So we can think of it as serving the layer above it and being served by the layer below it. It's broken down into 7 layers. So going from the top, you have the application layer, way at the top, all the way down to the transport layer. And then if you keep going further down, we have the network layer, the data link, and finally the physical layer. Oh, so I guess one other thing to mention is that there is the OSI model, but there are other models of networking as well, such as the TCP IP model, which is another framework that has gained a lot of popularity. When we're also thinking about the OSI versus TCP IP model, it's important to note that they're very similar, but in the case of the TCP IP model, we've actually combined the last 3 layers, the application, presentation, and session, to just be the generic, the general application layer. The other thing I really want to mention when it comes to the OSI layers is the concept of data encapsulation. So what is a unit of data that we are dealing with at each layer of the network? So as a packet traverses every single layer, an additional packet header may be added or removed in a process that is called encapsulation. And technically, we shouldn't even call it a packet because this unit of data is referred to as a packet when it's at the layer 3. But when we're further down, when we're at layer 2, it's technically an Ethernet frame. And when we're at layer 4, it's called a segment. So if we look at the slide a little more in detail, you can see, okay, so we have our actual payload of our application. If we progressively go like further down to further up, so at the frame layer, layer 2, our unique identifier is our destination and source MAC address. And then if we move further up, if we move further up and we move into the IP layer, our unique identifier at this point, and which is within our IP packet header, is the destination and source IP address. And if we move and traverse yet another layer and the IP header, packet header is stripped away, then we're dealing with the segment header. So note within the IP packet payload, we also have the segment header. In this case, we're dealing with port numbers as our unique identifier. So that is data encapsulation, but how do we actually receive and send any data? And that brings me to the next topic, which is a socket. It's an internal endpoint for sending or receiving data on a computer network. So how do we actually send or receive a segment, which is that unit of data at layer 4? We could use something called a stream socket, which is what we use for the TCP protocol, which provides a connection-oriented sequence flow of data. This is actually the underlying protocol for a lot of protocols that are at a higher layer, such as HTTP. There's, of course, the UDP protocol, the datagram, which uses a datagram socket, which provides a connectionless flow of data, which may actually arrive out of order. So I think there's a lot of use cases for UDP as well. I believe that DNS lookups frequently use the UDP protocol, for example, or NTP, which is how you synchronize a lot of clocks on different servers. But that is at the layer 4. What about if we're jumping further down? We're jumping down to layer 3 and dealing with packets, with those IP packet headers, or we're jumping down to layer 2 and we want to read those Ethernet frames. That brings us to a different type of unit called the raw socket. It's a socket, the same idea of something that allows us to have like an endpoint for receiving or sending data, but this time it allows us to send and receive data without that transport layer formatting. And in fact, there's something else I also want to highlight when we're talking about raw sockets. There's actually a difference between raw sockets and packet sockets. So the raw socket provides access to the layer 3 protocol, and whereas the packet socket provides that very key information about the link layer protocol. So it'll provide information about the source and destination MAC addresses. However, this is something that's frequently confused because both sockets, when we're opening both sockets, they're actually using underlying system calls with the same sock raw format. But when we're making the system calls, we're using a different property in each case. In the case of the raw socket, we're using the AF INET property, whereas in the case of the packet socket, we're using the AF packet property. So this might seem like a very specific thing, and it is, but it's relevant in our case because it became key when we were actually creating one network service where of course we were using raw sockets and we were making the socket syscall, but we really needed access to the link layer, so we had to use packet sockets. And then finally, there's actually another way, which we often forget, that we can also access that layer 2 information. We can use BPF interfaces, which are just another link layer interface that are available on different Unix-based systems. So if you're familiar with the utility TCP dump, super common way to debug different applications on different servers. TCP dump actually uses this Berkeley packet interface concept and uses BPF filters to sort of filter packets. And then finally, I guess one of the last networking concepts I want to talk about is protocols. So there are a lot of networking protocols which define a lot of what we do just on the internet in general, and also as a cloud hosting provider. So higher up within the application layer, there's like 2 protocols that we worked with, and honestly, most people, if they've ever used a website, they have dealt with the HTTP protocol. Also, if you ever set up your home router, you probably are using the DHCP protocol, such that your personal machine that connects to the internet on your home router is allocated an IP address. There's also the TCP and UDP protocol, something that I mentioned, which we're using when we are using TCP sockets or UDP datagram sockets at the layer 4. And we drop further down. Technically, a lot of people say the ARP protocol is actually a layer 2.5 protocol, so not necessarily just the data link layer. And then, of course, there's the Ethernet protocol. So this is probably extremely overwhelming. I agree, just because this is like stuff that it's taken me years to get really comfortable with, as I've written a lot more applications, and you might be overwhelmed like this adorable cat. You might be like, how can I wrap my head around this at all? But don't worry, the best way to learn is by doing. So that's exactly what we're going to do right now. We're going to look at examples of networking primitives that I've built both within the company and outside of the company, and look at some very simple code snippets to try to understand these concepts a little bit better and understand how we can use Go for this. So let's start with the load balancer. We're going to start with a layer 7 load balancer, however. So what is a load balancer? It essentially is a device that distributes traffic across a number of backends. Here's a little, I guess, diagram of it. You can see a user on the internet is trying to access a website, and perhaps there's a load balancer that is directing traffic to one of multiple backends. So how do we actually build the layer 7 load balancer in Go? This is something that if you've used Go or if you've ever used the HTTP package, you probably are already familiar with how to build a layer 7 load balancer. So very simply, you're using HTTP protocol, you're accepting client-side connections, and then you are passing a client-side request to one of the backends, and then you're returning a server response back to the client. Super easy. But one thing to highlight maybe is what is HTTP? Just in case, as long as we're really diving into definitions here, I'm going to dive into what exactly HTTP is. So it's an application layer 7 protocol. It's request response based. It is stateless, and it has a lot of different methods. There's the get method, the put method, the post method. But under the hood, it's actually using TCP or UDP sockets. Actually, one sec. Can we pause? Okay, continuing, let's look at the net HTTP package, which is really how we are building this layer 7 load balancer. So yeah, so step one, we are essentially using this concept of handle function, where we're creating a handler and listening and serving on port 8080. We're then going to accept an incoming request. And within our handler function, you see that once we get the request, we are reading it and then sending it to a particular backend, which is what we're doing in client.do. And then from the backend, we are actually returning this response back to our client. Super simple, very easy. But there might be cases in which we want to get a layer 4. We want to actually access what is on the layer 4. We will need a layer 4 load balancer. And when is this the case? In one case, sometimes it takes more resources to process all of our packet headers all the way up to layer 7. Furthermore, using a layer 4 load balancer could allow us to load balance packets of any type. So maybe we need something that maybe we're actually load balancing packets that are using the HTTP protocol higher up. And we don't actually have to care about what application protocol we're using since we're just using a layer 4 load balancer. So building a layer 4 load balancer, maybe a little more tricky just because I think in general, people frequently write HTTP servers, but they don't frequently write socket servers, which is what essentially we're using here. So for building a layer 4 load balancer, we will be using the TCP protocol. So we'll be using a streaming socket. We'll be accepting client-side connections, opening up a backend connection, and then using one Go routine to shuttle packets from the client to the backend, and use a second Go routine to shuttle packets from the backend to the client. So here in this case, you can see that we're using some of these concurrency primitives that I had earlier described as being super helpful in Go. So let's start. So what is TCP before we dive into this? Transmission Control Protocol. It's a connection-oriented protocol. It has 3 phases where a connection is established with a handshake. There's data transfer, and then the connection is terminated. And that is the protocol that we'll be using to create this load balancer. So once again, we're using the net package, as I had mentioned, not the net HTTP package. We are also going to be using the run package, which is a third-party package based actually on a Go standard library package called the sync package, but it builds upon this. So let's first start. So step 1, all we have to do is open and bind to a client TCP socket. So we're just opening right here. We're binding to a TCP socket to the specified IP address and port, and we're just waiting for incoming connections, which you can see within our for loop. Then when we actually have an incoming connection for that particular incoming connection, we're calling this handle con function, in which case we're actually opening a new TCP socket to the specified backend address. So we could actually be load balancing and picking which backend based on one of many different options. In this case, you could see that we are just randomly selecting a backend by using a pseudo random number generator in Go. Quite often, there's like a lot of different load balancing strategies that production ready load balancers will use. Great. So once we've done this, as I had mentioned, we'll be using two separate Go routines to shuttle packets back and forth between the client side and the server-side backends. So in this case, we're actually using the primitive called run groups, which is actually based upon the sync package. It's essentially a group of actor Go routines which implements a certain function and runs concurrently. So if one actor returns, all the Go routines are interrupted. So it's very similar to another concept we'll use later, which is the idea of a wait group and an error. A wait group and an error group, which is also, I believe, part of the Go standard library in the sync package. But in this case, we don't actually need to do any sort of context propagation for this to work. So you can see here, we actually have two run groups. We have one, which is copying data from the client connection to the backend connection, and then we have one copying data from the backend connection to the client connection. And within our copy function, we're essentially reading bytes of data and reading them from the incoming connection and writing it to the backend connection. Very simple. So this is obviously a fairly simplified load balancer, although even other TCP and layer 4 load balancers are using the TCP sockets and the TCP protocol. I think there's a few things. First of all, as I mentioned, we're using a totally randomized load balancing algorithm, but it might make sense to use something a bit smarter in the future, something such as IP hashing or round robin or equal distribution of incoming traffic across a variety of backend servers, or least connections, for example, sending a client to the backend connection with the least number of connections. Also, layer 4 balancers, load balancers, is usually a little more efficient. We aren't necessarily going to create a new backend connection for every single client connection. We could use like NAT or nmung incoming packets and then send them to the appropriate backend client as needed. So that was one layer 4 application. Now I'm going to dive into another layer 4 application called the port scanner. So I'm curious if any of you are familiar with something called Nmap. So Nmap is something else that we like to use. Quite often, you can use it to scan a network for any security vulnerabilities. It's a Linux utility that scans hosts and attempts to determine any open UDP or TCP ports. In our case, we are going to essentially be creating a port scanner that's very similar to Nmap, although we'll be creating this using Go. So for Nmap, we're also using the sync package. So how do we build this TCP port scanner? So also something to note here, you can technically use Nmap, I believe, to do UDP scanning as well, UDP port scanning. It's a little bit different than TCP because UDP is connectionless after all, so you're not holding open a connection. But for the purposes of this, we just decided to focus on TCP. So in our case, for the simple TCP port scanner, we're going to select a range of ports to scan. We're going to try to open and connect a TCP socket to a remote address and a port, and we're going to print the results. So let's start. So, opening and connecting to a TCP socket is a little bit similar as before. We're just specifying a host name and port, and we're dialing that host name and port with a particular timeout. Furthermore, once we've actually, once we've done that, we're also, as you can see, using wait groups and channels to try to make this a little bit more efficient. And in our case, we're actually using something called, I guess it's sort of our own semaphore, just to limit the number of concurrent Go routines that could be happening at the same time. So in this case, we are limiting the number of concurrent Go routines to 10 with the semaphore above by using a channel. So every time we actually enter a Go routine, or right before we enter a Go routine, rather, we're sending an empty structure to this channel, and then we are reading from the channel after we are done trying to open a TCP connection. And doing this, allows us to limit the number of Go routines that are running at the same time. So, as a quick summary, Nmap in real life, however, is actually checking for UDP and TCP ports on local or remote hosts. It also, goes beyond just port scanning. Unlike our very simple TCP port scanner here, it's doing host discovery. It often does OS detection. It often audits the security of a firewall. But for the example here, we've kept it a lot more simple, and I've just shown you how you can actually use a TCP socket, open a connection, and try to check for open ports. So now it's time to dive further down. And so let's start by jumping down to the layer 2 for our DHCP server. But before we go further, you might be like, what on earth? Earlier on, you told me that DHCP is technically a layer 7 protocol. Why are we considering this as a layer 2 microservice? And all of that is 100% valid. However, in this case, we actually jumped down to layer 2 because we wanted to use the packet sockets and access those MAC addresses in the Ethernet frame header in order to compare them to what was in the DCP packet payload to just validate the DHCP packets that we were receiving. So to do that, we had to jump down to layer 2. So first of all, what is DHCP protocol? I mentioned it before. It's a dynamic host configuration protocol. It's used by all routers to allocate IPv4 or IPv6 addresses to network interfaces. So DHCP v4 is using the ARP protocol, whereas DHCP v6 is also is using the NDP or Neighbor Discovery Protocol. It consists of a bunch of requests and responses between a client and a server. So the DHCP client, for example, on your virtual machine in a network or on your personal laptop in your home network, will first send a DHCP discover request to try to discover the DHCP server. The DHCP server will often send back an offer. Then there'll be a DHCP request. And then the server will acknowledge it, and your DHCP client at home will have a particularly allocated IP address. I do want to note that for IPv6, this changes a little bit. There's something called SLAAC, stateless auto configuration, which is a little different than what we'll be talking about today. But just for the purposes of this talk and this examples, I'm not going to talk about SLAAC. So, as I mentioned, we needed those link layer MAC addresses for validation purposes. So for our DHCP server, we were doing a couple things. We were using raw sockets this time. So we're opening and binding a raw socket to a particular interface. We were reading data from that socket into a bytes buffer. We were unmarshalling all of the data into a DHCP message and retrieving the sender hardware address. We were then comparing the sender hardware address to what actually was in our Ethernet frame header. Then we were switching between the handlers based on the message type, and then we were unicasting a response back to the sender, our DHCP client. So in this case, we're using a couple of different packages. So we're using the raw package created by my former colleague, Matt Layer, which was dealing with raw sockets. So within the raw package, what's super interesting is if you dive down, you can see what we're really doing is making a bunch of syscalls using the Unix package. So in this case, we are making a syscall to open a packet socket, as you can see right here. And then we are reading from that packet socket. One other interesting thing though is that's what we were actually doing on Linux machines. However, on BSD machines, we weren't actually using packet sockets. We were using BPF interfaces instead. So this is something fun that I also want to mention about Go. I think Go is extremely it's quite often easy to really dive into underlying packages within the standard library, or outside of the standard library, to see actually what's happening under the hood. So I think that facilitates a lot of learning for onboarding engineers to systems teams. So the three packages that we definitely are using in this example are the syscall package, which is what's being used within MATLAYER's raw package, the OS package, as well as the Unix package. So all three of these are allowing us to, either open the BPF interfaces or make syscalls to open raw packet sockets, or even check the operating system that we're on. So when we're actually creating the DHCP server, step one will be opening and binding to a raw socket. So you can see that's what's happening right here. We're not actually setting any timeouts, but we're opening, binding to this raw socket, and state that we're expecting to receive IPv4 type packets. We are then reading data into a buffer, but then we're sending that data that we've read into the buffer, like a worker is actually reading from the buffer and handling the requests. So note that we're also limiting the number of concurrent workers by, once again, using that idea of a channel. So you can see right at the top, we are creating a channel of requests, which is, just has a particular number of workers, and then we are just reading from the channel, like for each, we are reading from the channel. Each of those workers is reading from the channel. So the other thing I want to note is within our DHCP server, we're also validating DHCP requests. And this was the main reason why we even dropped down to layer 2. We were, as you can see, we're actually reading what that Ethernet frame header MAC address is, and we are comparing it to what we are seeing in our DHCP packet. And if they're not equal, we're actually returning a particular not acknowledged message type back to we're broadcasting it back to our client. And then finally, as I probably skipped over myself, finally, we're actually building and sending that response back. So the summary for our DHCP service is that the service I've talked about here uses the dynamic host configuration protocol. It's used to dynamically assign IP addresses. It's used in a number of places, including your home routers. We're using raw sockets here. Well, I guess technically we're using raw sockets, but we're also under the hood, we're using BPF interfaces. And in this case, even though DHCP is a layer 7 protocol, we're jumping down to the link layer or layer 2 to do source MAC validation. So I realize that I've gone through a lot today, but if there's anything you've learned from this, it should just be a few key points. First of all, Go can be great for building network primitives. Not always, but in a lot of use cases, it can be perfect. Second of all, there's a bunch of layers of, I guess, the network model. There's for layer 7 in Go, you can use the net/HTTP package. If you're jumping down to layer 4, you can use the net package, which lets you open TCP or UDP sockets to send and receive data. If you're jumping down even further to layer 3 or layer 2, you can use the raw package, MATLAYER's raw package, which under the hood is actually using the OS package, the syscall package, and the Unix package. So really, if you absolutely need to do your own thing in Go, it's very easy to create your own packages by just using the syscall package and like making whatever syscalls you need to. Finally, I guess the last thing to mention is that there's a lot of good concurrency primitives in Go, which are very handy when writing networking services where you often are, reading a lot of data, like at the same time using a number of workers. There's the sync package, there's the run package, which uses the actor models so you can have concurrent Go routines. There's just the concept of Go routines, the lightweight processes, and then finally there's channels. Super useful. Channels you can actually use to send and receive data, but in our case, we're actually sending empty structures to a channel to kind of use as a semaphore to limit the amount of workers that we could have spinning off at a particular time. So thank you. Hopefully you've learned something about Go and you're just as excited as I am about networking in Go. And of course, I couldn't have learned any of this without a lot of mentors and people that have helped me from my team. Thank you.